Do you have a, like, can you hit your record button and let me see what it asked me on this side?
I just did it. I think it says, please ask the host to give me permission to record.
Oh, I think I will have to turn over, like, make you the host or something.
Oh, okay.
Yeah.
Okay.
But I'm going to chop this up. I'll have it up today, I promise, because this is my last class. And so I'm going to spend the rest of the afternoon getting those videos chopped up and uploaded. So it'll be up to you. You'll be straight.
Okay, thank you.
All right.
Dr. Russell, is this all we're doing today? Just
What
the
you mean?
practice problems?
Yeah.
Like, okay, so that's all we're focusing on today?
Yeah. What else did you want to do?
Well, no, like, you know how last time you were just, it was kind of like the whiteboard, you was, you know.
Yeah, no, we're going to,
stuff.
but the practice problems, I'm going to be writing on here too.
Okay.
Yeah, so we're gonna be good.
Dr. Russell.
Yes.
Okay, so it's a first module and then it's first module 1A. Should we have completed both pre-assessments and both of them by now?
No, because we haven't got to the next module. We're still in the first one.
Okay, so
okay, that's the same thing.
Yeah, so the modules, if it's 1 and 1A, when we get to 1A, it's a totally different topic. And so by that time, then once we start that topic, that subject matter, then you do the pre-assessment and the quizzes and the readings and all that.
So that'll be for next week then?
Probably so, or Friday, depending on how far we get today.
Okay.
Yeah.
So I have a question.
Go ahead.
I'm just trying to get clarification, like how your class flows. Like you want us to like read the chapter first and then watch your videos and then take the quizzes and all that, or?
Well, it really, that's up to you, the order that you want to do it in. But you definitely should be reading those sections that are in the syllabus. Whether you read them prior to watching a video or after watching a video to reinforce it, it's up to you. It's totally up to you.
Okay.
Yep.
Thank you.
But when I send those videos out, my suggestion would be, like, of course, you're not going to always have time to do it right that moment, but do it sometime that day and take notes. And then you can look at the sections in the book and compare what you did, you know, and then, but the quizzes, I think, once I send out the actual video, I would take the quiz after watching the video while the information is still fresh.
Okay.
Because the quizzes are kind of tailored to what was in the videos.
Okay,
that's a good question. Yeah, no problem. Anybody else got a question about anything?
Dr. Russell.
Go ahead.
Is the textbook in the bookstore?
Well, I have to put an order in because I knew we were going to be virtual and I really didn't know how many people were going to be on campus versus being away. So I didn't put in a textbook order directly, even though I sent the numbers over the summer. So there may not be copies in there. If you're on campus, actually, I think I did a poll. Did y'all finish that poll that I sent out about whether you're on or off campus? Because I can base the numbers on that if you completed it. If you haven't, go back into Blackboard and look at the announcements from, I think it was the day before class started or something like that. And there's a Google poll, a link in there that I sent out to ask who was on campus, who was off campus, so on and so forth. But if you went to the bookstore, they can still order you a book. Whether, it may take a while to get there, but they can order it. My suggestion is to go a different route. You can find that third edition now anywhere, and you're probably gonna find it for cheaper than it is in the bookstore. And if you get an ebook, that's fine too. It doesn't matter to me.
So for some of the people who ordered their books within these past couple of days, I know they're not gonna get here as soon as possible because of shipping and the virus and whatever.
Yeah.
So I'm probably gonna have to catch up on some of the sections and chapters.
That's fine, but that's why we're gonna do work here, and you'll also have those videos to refer to, as well as, you can use that other website that I showed y'all, Master Organic Chemistry. It's a lot of resources that you can use in the meantime, with these different topics that we're doing, even if you don't have a book.
Okay.
So you'll be good. Don't panic. You straight.
I just like to be ahead of everything.
I understand that. That's good. You always want to be proactive, not reactive. So that's good.
Okay, I have one more question.
Go ahead.
In the syllabus, there are some sections that are highlighted in yellow. Are
Yeah.
those ones that we need to read, and the other ones are like kind of optional?
No. It's no
Or
option.
what's the
It might have
difference?
just been an oversight on my part.
Oh, okay.
If there's a section number associated with the topic, read it. Yeah. Because I think on the syllabus, I may have highlighted, I know I highlighted the questions at the end, like the practice problems. I
Mhm.
always highlighted that, but those highlights don't mean one section is more important than another. All of them are equally important. That's a good question. Any other questions? What did y'all, while I got people here and we kind of warming up, what did y'all think about how Friday went?
It went well.
Yeah, okay. I thought we had a good class. I mean, it's always different when you're not on the whiteboard and in the presence of human beings. So I always try to make sure that it's not just me talking, right? So that's what we're gonna do today. So we got a couple of skills that we're gonna work on today. Obviously, if you look at that first question, it's talking about skeletal structures or skeletal forms. I'm not sure if I sent that video or not, but we do have, there is a video. I'm gonna send it after class if I didn't send it already. But there's a video talking about skeletal forms. Now, why is this important? Let me go back to, a blank page real quick. So remember when we were talking about carbon and we were saying, we were saying that carbon can form all these different types of bonds and things like that. But we also talked about geometries, right? We talked about carbon, if it was sp3, then it had a tetrahedral geometry. Do y'all remember that? And then if it's sp2, then it's trigonal. And then if it was sp, we didn't talk about, I forgot to mention that because I think we ran out of time, but sp is linear. Did we do sp hybridization? Like an example?
I don't believe so.
I can't remember. I don't think we did. I know we did sp3 and sp2. So for sp, let me go back to that page of notes. And then, let's see. Right here. Yeah, so we did sp2, we did sp3, but I don't think we did sp. So sp hybridization, can y'all see my screen still?
Yeah.
Yeah.
Okay, bet. So sp hybridization is when you take the 2s and one of the two p's, right? Remember the two atomic orbitals you add together, you're gonna get two hybrids. So you get two sp hybrids and then two unhybridized p orbitals. So a carbon that's sp hybridized, let me just go down here. If it's sp hybridized, it's gonna have a hybrid here. It's gonna have a hybrid here, but then it's gonna have two unhybridized p orbitals that kind of form like a envelope around it. So one of them is going to be vertical like that, and then the other one is going to be horizontal like that, kind of coming out of the page at you, right? And so remember when we talked about hybridized overlap and unhybridized overlap, if this was to overlap with another carbon that was also sp hybridized, oh, that's not right. Right? If it was a hybrid overlap with this type of carbon right here, right? What would happen when these two orbitals overlap? What kind of bond would you get?
Covalent.
A covalent bond, yes, I agree with that. But what type? Would it be a sigma bond? Would it be a pi bond?
Sigma.
A sigma bond, right? Remember, sigma bonds always come from overlap of hybrid orbitals, right? So this will give you a sigma bond, and then so would that. The other hybrid, that's kind of, let me get this tiles out of the way. Right, the other sigma bond will be also give you, the other hybrid back here would also give you a sigma bond, right? And this is a sp hybridized carbon. All right. So what about those unhybridized p orbitals when they overlap? Like, right, let me fix this because I don't like that. Right, so the unhybridized overlap is going to come from here, right? Between these two, is that right? And then between these two. So it's actually going to form like a cylinder around those carbons. What kind of bonds do we get from that when unhybridized p orbitals overlap?
Pi bonds.
Pi bonds, right? So sp hybridized carbon is going to have 4 bonds, right? We talked about that. 2 of them are going to be sigma bonds, and then 2 are going to be pi bonds. For a total of 4 bonds. All right, and the geometry is linear, and the bond angle is, let me fix that. The bond angle is 180 degrees. All right, so it's linear and a 180 degree bond angle, 2 sigma bonds and 2 pi bonds. So in this particular case, this is where your triple bonds would come from. Can you see that this has, like this carbon right here has 2 groups attached. It's got a group attached here and also has a group attached here. So it's got 2 groups attached to it. Because remember, we talked about hybridization, we talked about either looking at the number of groups attached or the number of pi bonds, right? We talked about both ways being ways to identify the hybridization state of any atom. Is that okay?
Yes.
Any questions? No questions. All right.
Can you go back up, Dr. Russell, so I can see the picture? Please.
Right here?
Yes, thank you.
Mm-hmm. Yeah, so that sp hybridization, it's like that carbon, if I was able to draw it in 3D, it would look like it has like a fan around it, like fan blades. The 2 p orbitals, one of them is vertical, one is horizontal like that. And that's where that linear geometry comes from. It's cylindrical. It's almost like a cylinder. So it would look something like, sorry about that, like this, right? With a carbon on each end of that cylinder. All right. Sorry about that. Any questions about the hybridization states? So sp3, sp2, and sp are your 3 hybridization states, and then tetrahedral, trigonal, and linear are your geometries. And the reason I'm talking about that is because if when we go from drawing skeletal forms from Lewis forms, let me show you that. So here's a Lewis structure. Let's say I have because carbon can form all these different types of chains and rings and things like that. So let's say I have a 3 carbon chain like this, right? This is propane, by the way. And I'm going to sneak in some nomenclature to you. You know, I don't like teaching nomenclature just as a section because it's boring. So I'm going to sneak it in when I can. So this is propane. Pro meaning 3 carbons. Right? And ane meaning all single bonds. That's what the ane means, like the suffix. So the pro part is 3 carbons, and then the ane is all single bonds. So you got 3 carbons bonded together with all single bonds. Right? You can write this 3 different ways. You can write it like this, which is the Lewis form. right? My handwriting sucks today. Well, every day, but today is even worse. Right? This is the Lewis form where you show all the bonds, right, to all the atoms. All right? You could also write this in what's called a skeletal form, right? And the way you do that is you don't show the carbons, right? You only show the bonds, right? So everywhere on this line, there are three, I'm just gonna put 3 dots for now, right? Those 3 dots are your carbons. If it's a vertex like this, that's gonna be a CH2. Right? If it's a terminus like this, that's going to be a CH3. Right? Keep in mind, unless another atom is there, hydrogen is understood to be on that carbon, unless we put another atom there. When we get to the examples, you'll see what I'm talking about. But every vertex where 2 lines comes together is a CH2. Every end of a line or terminus is a CH3. Right? And in a skeletal form, you do not have to show the hydrogens. You don't show any of that stuff, right? You just write it out. Now, the question is, why did I write it like that and not like that? Somebody help me out. Why is it important to understand the geometry of carbon or whatever atom you're working with? Anybody?
Is it to know how they're orbiting, maybe?
Yeah, you want to know that, but you also know that the geometry is going to give the molecule a shape, right?
Yeah.
Yeah. So when I draw it like this, I have no idea that those carbons are tetrahedrons, right? Or tetrahedrons. But if I draw it like this, let me show you this. So here, there's a hydrogen here, and there's a hydrogen here. The reason I draw it in a zigzag like that is because I'm taking the geometry of carbon into account. Right?
Won't that also let you know how many what type of bonds it is, like if it's double or single bonds or something like that?
Well, yeah, you can put in a double. I'm gonna do another example that has a double bond in it. But yeah, you will be able to, if you have a double bond present in a skeletal form, then you got to put it in as 2 lines. I'm gonna show you. That's a good question. I'll show you an example of that.
Dr. Russ, can you go up to the propane really quick?
Right here.
Yeah.
Okay. So any questions about that so far? So this is a Lewis form, and then I showed you a skeletal form, and then I'm gonna show you the condensed form. Once we learn those 3 different forms, we're gonna go to some of those examples and start banging them out. So any questions about the Lewis form? I'm gonna do it. We'll do propane, and we'll do a larger example so that the skeletal part will look a little bit more, it'll be easier to see what I'm talking about with this geometry.
Okay, I'm done.
All right. So if I wanted to condense that, the condensed form, you don't show any bonds, right? You just show the atoms. And we're gonna do some examples of that too. There's a bunch of examples on that handout, right? So this is the condensed form. All the atoms are bunched in together, no bonds, no lines, nothing. But you can interchange between condensed and skeletal and Lewis, right? They're all interchangeable and they're all equal. There's no one depiction that's more important than the other one. All right, let's do another one. Let's do a 6 carbon chain. So I'm gonna write that out. Let me show you something too right quick. Give me a second. All right, so if you can see my screen, no, you cannot. Or you see my camera. Let me pull this up, make sure you can see me. Yeah, so on my camera, this little notebook right here, somebody sent this to me from Amazon. And on the inside, because people struggle with these drawing the skeletal form and stuff like that. On the inside, can you see the pages, how they have like those little hexagons locked together on that page?
Yeah.
Yes.
So that this notebook is designed to help strengthen your structure drawing skills, right? It forces you to know the geometry and to follow the proper geometry, right? So all these little lines right here, these little locked in hexagons, if you were drawing skeletal forms, it helps to kind of build your muscle memory on how to draw the lines and things like that. So I'll have
What's
to
the
go,
name of it?
yeah, I'll go back and look at it's right here. It's called, this is where you order it from. It's called Enchanted Willow. That's the name of the notebook. And I was blown away when she sent me this because I'd never seen anything like it before. It's called Enchanted Willow, and I think the notebook costs like $5, but it's worth it if you want to practice drawing your structures out in skeletal form, right? And this is on the cover. This is LSD, by the way. Don't ever take this. It'll break your brain. All right. So let me go back to here. So we're doing, I said 6 carbons, right? So we're doing 6 carbons. I'm gonna put all the hydrogens in here. You can imagine how cumbersome this is, right? Having to write all these hydrogens out and all this stuff it's a pain in the butt. Right? So I got 6 carbons. This is the parent name for a 6 carbon chain is hexane. Right? Hex meaning it's the Greek prefix for 6, and then ane meaning all single bonds. All right? So that's 6 carbons bonded together with all single bonds. A compound like this, we call it saturated. Right? There's a difference in saturated and unsaturated. Saturated means that all of the spaces on carbons, if it's not bonded to another carbon, it's bonded to hydrogen. So it would be considered saturated. You heard the term like saturated fats. Those are fatty acids that don't have any double bonds in them. And unsaturated fats are the opposite. They are fatty acids that have double bonds in them somewhere on the chain. All right. Let me see if I can pull up an example. Hold up, because I want to make that point. My internet is bootleg too, by the way. But let me see if I can find an image of a saturated fatty acid. Here we go. I want the other one though, the skeletal form. I guess this will work. Can y'all see that? So how this is what's called a saturated fat. You see the carbon chain in the fatty acid is all single bonds. And then down here it's unsaturated. Like you have a double bond in there somewhere. Doesn't matter where it is. Right? But there's a difference between saturated and unsaturated fats. The saturation just simply means that on every carbon, all of your bonds are taken up by either hydrogens or other carbons. Unsaturated, here you have at least one space where that's not the case, right? So you have these 2 carbons have 2 less hydrogens on them, right, than they would if that double bond wasn't there. So it's considered unsaturated. That's why saturated fats are so bad for you, because if there's nothing in the chain to change the shape, those chains just kind of stack on top of one another through van der Waals interactions. And that's bad. That's how your arteries get clogged up. All right. Any questions so far? I wouldn't have been able to do that if we were in the classroom. So I kind of like, come on down. There we go. All right. So now we have hexane. How would you draw the skeletal form for that? let's think about it now. I want six carbons. I got to take the geometry into account, right? And so there's a shortcut or a little rule of thumb that I came up with to help you with these skeletal forms. If it's 6 carbons, then that means it's going to be 5 pencil strokes or pen strokes if you're using a pen, right? And it has to be in a zigzag. And the reason is because what? Why do I have to draw it in a zigzag fashion?
To account for the different carbons. Each point is the carbon.
Yes, every carbon has what shape? If it's sp3, it's a tetrahedral, right?
Tetrahedron, yeah.
It's a tetrahedron. So every carbon is a tetrahedron. So I have to account for that. All right. So now this is 1, 2, 3, 4, 5, 6 carbons, 5 pencil strokes. If you can count the strokes, 1, 2, don't do that. 2, 3, 4, 5, like that. All right. So I got 6 carbons in that chain. What's at each vertex? Right. This is all of these vertices.
Carbon.
Right here, 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 and here. Those are vertices, right? What's at each vertex?
CH2.
A CH2. And then these are termini, right? The end of each line, which will be what?
CH3.
CH3. Good. So that's the skeletal form. All right. How would you condense that? What would you do to draw the condensed form for that? Right. The good thing about drawing condensed forms is that you can actually condense it. How many CH2s are in that chain?
4.
4.
4 of them. 2, 3, 4. And then you got 2 CH3s at either end, right? So if I wanted to condense that down, I could write it like this. So I'll write CH3. Come on. Sorry. And then I can put those 4 CH2s in parentheses and put a subscript down here. Right? Notice the subscript is 4, and that corresponds to the number of CH2s that were in the chain. And then I put another CH3 here at the end of the chain. Of course, you can write that out. You can write it out like this. And that would also be considered the condensed form. All right.
I have a question.
Go ahead.
How did you know it was like CH2 and all that? Like for the vertex?
Mm-hmm.
How did
I know it was hydrogen and not something else?
Yeah.
Okay, so let's go back to the very beginning. How many bonds can carbon form? Every carbon has the capacity of forming 4 bonds. Is that right?
Yes.
So let's take this carbon right here. It's got a bond to it on that side and one on that side. Is that right?
Yes.
So that's 2 of your bonds used up out of 4.
Okay.
You following?
Yeah, you have 2 left.
So I got 2 bonds left. If nothing else is on that carbon, no other atoms like chlorine or fluorine or oxygen, if nothing else is on there, the 2 groups that are left are understood to be hydrogen. Right, so these the remaining 2 groups are understood to be hydrogen. Always.
Okay.
Yep. Did that answer it?
Yes.
Yeah. Anytime you have a chain, every vertex is a CH2.
So then when you got CH3, how did you?
Again, excuse me, you got to have 4 bonds to carbon, right?
Yeah.
Let's take this end down here. Right? How many bonds does this carbon already have?
Just 1.
Just 1. So you need 3 more bonds to it. And since there are no other atoms attached, the other 3 bonds are understood to be hydrogen.
Okay, I get it. Thank you.
Good question. Hush. All right. Any questions about this so far? No? All right. Let's go to the handout and let's do some of those examples then. All right. So what would you do in that first example in A? It says convert each skeletal form. I didn't write that. I don't know who wrote that on the screen. Convert each skeletal form, convert each molecule into a skeletal form. What would you do? First thing we need to figure out is how many. Okay, so here's the thing, the method that we're going to use. We're going to find the longest chain. Right, the longest continuous chain. That's what we gotta find that. Once we do that, everything else becomes cake. All right. So in here, you can see that there's a chain of 4 carbons right there. Am I right?
Yes.
So let's draw that out. So 1, 2, 3. That's my 4 carbons that are in that backbone. Remember, it's always one less stroke, right? So 4 carbons will be 3 strokes of your pencil. And it has to be in a zigzag because carbon is tetrahedral. Are you following?
Yes.
Yes.
So the 2 middle carbons right here are CH2s, right? Those are your 2 CH2s. And then on the end, we're going to say that those are the CHs. But look at the CH on this back end right here. What's attached to it? You see the subscript right here?
So that means it's 2 of them.
2 of those CH3s are attached to that end carbon. So let's draw that in. So we're going to put 1 here and we're going to put 1 here, like that. Is that okay?
Yes.
Yeah.
And then what about the other end? It's the same
You have
thing.
to do the same thing.
Mm-hmm. You do the same thing there. So we're going to put 1 here and 1 here. Is that okay? Yes or no?
Yes. Yes.
So that's how we can take that condensed form and turn it into a skeletal form. Now let's count up, because the longest chain was not 4 carbons. Let's count 1, 2, 3, 4, 5, 6. You see that? We got 6 carbons.
Can you do that again?
Okay, let me erase the highlights. Never mind.
What about the CHs and not CH2?
Good question. So these were considered, excuse me, these were your CHs right here, yeah?
Mm-hmm.
Now tell me why that's a CH. How many bonds does it have to it that you can see?
That's 3.
3. So the last bond has to be by default what?
Hydrogen.
Hydrogen. And since it's skeletal, you don't have to show it.
Okay.
Right? So the anytime you're in question about or in doubt about what an atom, what the carbon is, if it's a CH or a CH2, count the bonds that you can see, and then the ones you can't see, they're understood to be hydrogen.
Okay.
Does that make sense?
Yes.
So are you saying that the last bond is hydrogen by default, or like only the ones that you can't see?
No, just the ones you can't see, because the last atom here, that's a terminus, right? So that's understood to be a CH3. The end of every line is a CH3, and anywhere 2 lines come together is a CH2, unless there's another atom attached to it. Does that make sense?
Dr. Russell,
Go ahead.
what are the ones you circled in blue? What are those? Those aren't CH3? No.
No, that's a CH.
That's just CH, and then okay. So the terminal
Yes,
thing
it's
is
a CH3.
the ones
So
on
this
the
is
end.
a CH3 up here. Following?
Uh-huh.
That's a CH3, and so is that.
Okay. Okay.
That's important. I'm glad y'all asking these questions because this is all foundational stuff. If you get this and can get it absorbed, then when we do harder examples, the basic stuff won't trip you up. So that's why I'm spending time on this, because there are a lot of skills that we can learn just from looking at these examples, right? So we got a 6-carbon chain. Is anybody thinking about the backbone? Like what are these CH3 groups that are here that are not a part of the longest chain? Write this down. Those are called what you call substituents. Watch me run out of room. Those are substituents. That's any atom that is not a part of your longest carbon chain is called a substituent. Obviously, I don't have room to write all of that out, but it's any atom that is not a part of the longest continuous chain of carbons. Right? I don't know who is writing in green on the screen, just scribbling.
I got a question.
Go ahead.
So I understand for this problem, we're only working with like the carbon and the hydrogens, and I see at the bottom it has like oxygen in it.
Oh,
so can you write?
We're gonna
so
hit
you
it.
can have this skeletal structure of like any type of.
Yeah.
Oh, okay.
Anything. You can convert any condensed form or any Lewis structure into a skeleton. We're gonna do we're doing more than just these. We still got 20 minutes left.
Okay.
Yeah.
Can you give the definition of substituents again?
It's any group that's attached to the longest continuous carbon chain, but it's not a part of the chain, right? Can you see how here, let me just kind of highlight this. Let me erase that. Uh-oh, never mind. Let me just highlight it. So here's your longest continuous chain right here, right? And do you see how those CH3 groups that are attached on both ends, how they're kind of not counted in that longest chain?
Mm-hmm.
So they're on the backbone, but they're not a part of the backbone. So we call them substituents.
Oh, okay, thank you.
Mm-hmm.
I'm sorry, Dr. Rush. Could you
ahead.
say the definition one more time? Or like just write it underneath it a little bit?
I'm trying to, there we go. I'll put it right here. So you got the word down
Thank
here,
you.
right?
Yes.
So we're going to say any group attached to the longest continuous carbon chain. I'm saying continuous chain now too, because that matters. Any group attached to the longest continuous chain will be a substituent.
I have a question.
Go ahead.
So I'm kind of confused still on the CH. If those CH3s wasn't attached, like how would it look? It would just be like the end.
Say that again now. If the CH3s weren't attached, is that what you're asking?
Yes. How would the CH be left?
Well, it wouldn't be a CH if the CH3s weren't there.
Okay.
It's only a CH because, okay, let me give you an example. So here's a carbon, right? Under normal circumstances, that carbon is going to have 4 hydrogens attached to it. Right? Remember, it wants to have 4 bonds because of the octet rule. Are you following me?
Yes.
So if I take off 2 of those hydrogens, right, and replace it with some other atoms, do you see how it turns into a CH2? Because I took 2 of the spaces up with something else.
Yeah, I see it.
And if I took off 3 of those atoms, you see how it becomes a CH when I fill up 3 of those spaces with something else?
Mm-hmm.
Yeah. Or if I only took off 1 of the atoms, right? You see how it's a CH3 now because only 1 of the spaces is taken up by something else.
Okay.
Does that make sense?
Yes.
Okay. Let's do another one. Okay, so let me go back real quick. If the longest chain is 6 carbons, what's the name of that?
Hexane.
Hexane. If it's so, I'm gonna give you 1 to 6 for now. So 1 is methane, 2 is ethane, 3 is propane, 4 is butane, 5 is pentane, and then 6 is hexane. So those Greek prefixes, that's what you use to determine what the numbers are. So it's meth, and then F, and then prop, and then bute. Bute is 4, and then pent, which is 5, and then hex. Those are your prefixes for chain lengths of 1 through 6. And then you put the ane on the end to indicate that it's all single bonds. So methane, ethane, propane, butane, pentane, and hexane. All right. Any questions about that? Let's do a harder example with more atoms that are not carbon.
This is kind of off topic, but the ENE, what does that one stand for?
That tells you that there's a double bond present.
Okay, okay.
That's a good question.
Okay.
Very good question. I think there's one in here with a double bond that we're going to do. And I'll talk a little bit about that too. Because like I said, I don't want to just do a whole unit on nomenclature. I'd rather just sneak it to you in bits and pieces.
So all of these that you gave us, these are like the long, well, are they like chains of carbon?
So methane.
Single bond carbon?
Yeah, so methane is 1 carbon with 4 hydrogens on it. Like that. Ethane would be 2 carbons. Right, so 2 CH3s connected together. Following? Yes, no?
Oh, yes, I thought I unmuted myself. Yes.
All right. Propane would be 3 carbons, right? Ran out of room. Right, propane would be 3 carbons. And then you fill in the spaces with hydrogen so that every one of those carbons has 4 bonds to it.
Oh, okay. All right.
And then butane would be 4 carbons. And you fill all the spaces in with hydrogen so that all your carbons have 4 bonds.
I get it.
Yeah, yeah. And then 5 and 6. So I got you from 1 up to 6. And then we'll keep sneaking them in.
Okay, and they just like the strands of carbon with the single bonds too.
That's all we're doing right now is just single bond, all single bonds, which the class of compounds that we're talking about are alkanes, A-L-K-A-N-E-S, alkanes. That's all carbon, carbon, and carbon hydrogen single bonds. See the A-N-E? That means all single bonds, just like propane, ethane, butane, so on and so forth. If it ends in A and E, that means it's all single bonds. Everybody okay?
Yes, sir.
It's good discussion. I don't like lecturing. I like engagement, so this is good. Let's do another example. Actually, we're gonna do these other 2 examples because we got time. So what would you do with B? I'll come back to that top example too because I want to drop in another nugget about that chain, about those substituents attached to it.
Are we supposed to finish this sheet?
We're not gonna finish it. We may not do every problem, but we're gonna do selected problems that are highlighted.
Okay.
Yeah.
And another thing, so these are just our practice problems for us to practice right at the end before the test or after the test. We're not submitting this.
This is gonna be submitted.
This is gonna be submitted.
Anything that's in Blackboard, that's a handout, you're gonna submit.
Okay, so you want this on a separate sheet of paper or something? Like
you can write on what you have. You can print it, and write out the questions. You can handwrite them. You can write on your screen and save it as a PDF, however you want to do it. But this is, remember we talked about what the homework is? This is the homework. That's why we do it in class, so I send the videos out.
Okay.
So we only do the problems that we do in class. Like we don't do, say if we don't do it in class, we don't do it at all.
Huh? I don't know. I'm not sure if I'm getting that. So
okay, say if we skip over C and say if we just do A and B in part 1.64, is that all we do? We don't
when you turn it in, yeah, that's all you're responsible for.
Okay.
But that doesn't mean that you shouldn't try other problems though. Because
Yes,
it's
sir.
just like with anything, right? The more reps you do, the better you become. It's all about reps. But
Okay, and like when class is over, like when are you just gonna sit? Like I know you're recording the lectures, so like, are they gonna be just on a
on
specific
YouTube.
folder, like on Blackboard? Oh, it's on
No,
YouTube. Okay.
I'm putting on YouTube because there's not enough space to hold the videos on Blackboard.
Okay.
But I already have a channel created. I just need to chop the videos up into 15-minute blocks so I can upload it. But I'll be doing that today for Friday of last week and today.
Okay. Okay. Thank you.
And you said there's no deadline for the YouTube quizzes?
The deadline is, so when I send the videos, the object is for you to watch it and then go take the quiz. By the time we get to the first exam, those quizzes are going to be taken down. All that stuff is going to be taken down. So if you had to impose a deadline, I would say to have it all done before you take the first exam.
Okay, thank you.
All right, are we ready to do B?
Yes.
So B is it's not really tricky, but there's some concepts that we need to understand before we do it. So first of all, excuse me, do you see how this CL is to the right of the CH and it's in parentheses?
Yes.
That means it's bonded to that carbon and not this one. It's not bonded to that one. Right? The substituent or the group that's attached to that carbon, this CH right here, is always going to be to the right of it, and it'll be in parentheses. Right? And then what about the OH? Which carbon do you think that's bonded to?
The CH.
This one, right? Because it's to the right of it, and it's in parentheses, so that means it's bonded to that carbon. So how many carbons do we have in that chain total?
4.
4 carbons. So let's write that down. I'm gonna write it in Lewis form first because I want to make the point about what's bonded to what. So here we got 4 carbons. I know it asks for skeletal form, but I'm gonna write it in Lewis form first, and then we're gonna convert it. And as a habit, I would do that for now until you get the hang of identifying the chains and then being able to write them out right away. I would write the Lewis form out anyway, just because. Right, because right
Dr.
now,
Rizzo?
yes.
That's a question, quick question. So are like if you have like CH and it's bonded to something, is it supposed to be on the right in parentheses or is it supposed to be on the left? I'm confused.
Well,
like you said, that Cl bonded to
it's bonded to the carbon to the left of it.
Right.
Yeah, but the Cl is on the right of the carbon that is bonded to.
Uh-huh.
So I was looking at the chlorine, not the carbon.
Right. So the chlorine is bonded to the CH.
Yeah, right here. This
right
one.
here. Yeah, the first. Okay.
Now,
and then the second CH is bonded to the OH right next to.
Yeah,
Okay.
just because the OH is to the right of it.
Okay. All right.
See
Okay.
that?
I get it. Okay.
Okay. All right. So now this is, I'm just going to put the hydrogens in here. That's a CH3. Everybody agree with that? And then this is a CH3. Yeah?
Yes.
And then the next carbon has a chlorine on it and an H here. You see how it's a CH? Because 3 of the spaces are taken up by other stuff.
Yeah.
Yeah.
And then this one has a OH attached to it, like that. Following that? Let me tell you what somebody's thinking. Why didn't I put the OH on the bottom or the Cl on the bottom? It doesn't matter. You can put them on the bottom or the top because there's no stereochemistry indicated where one has to be up or down, so it doesn't matter. Now, how are we going to turn that into a skeletal structure? What would you do?
You'd start with your like your chain of carbon.
Start with the carbon chain. Don't worry about what's attached. Oh, what is chlorine, by the way? What's the term that we just learned for that?
Substitute.
Substituent. So it's OH, right?
Yes.
Good. You see, anytime I introduce a topic, I'm gonna try to find a way to bring you back to that topic. So all these examples are going, once we learn a topic, every example is going to have some way of reinforcement. All right. So if you're paying attention and taking notes and asking questions, I promise you, you're going to learn a lot. All right. So the chlorine and the OH are substituents. So you said, who was that, by the way, that said draw the chain first?
Oh, that was Amari.
Okay, good. All right. So we're going to draw the chain out. 4 carbons. How many strokes?
3.
3.
I'm gonna put it right here. 1, 2, 3. Boom. You see that?
Yes.
You see the 2 vertices? Those are your CHs. Yes. And the 2 N carbons are your CH3s. Yes or no?
Yes. Yes.
So which carbon had the chlorine on it? Was it this one right here or this one right here?
The first one.
The first one, right? Right here. So I'm gonna put the chlorine right there. Following that? And then I'm gonna take the other carbon. I'm gonna draw it down here so you can at least see it. And I'm gonna put the OH right there. Is that right?
Yes.
Same structure, same compound, just drawn a different way. What's also on that carbon with chlorine? What am I not seeing?
Hydrogen.
Hydrogen. And you don't have to show that, right? Because it's a skeletal form. Does that make sense?
Yes.
Yeah.
All right. Let's do that ring D. Because that's a good
I have a question.
Go ahead.
Quick. Why was the CH3 drawn down? Like when we did the terminal, it's down instead of up like the last one.
It doesn't matter. It's all semantics. You mean you want to draw your chain like that? One of them was going to be down either way, right?
Yeah.
So it's symmetrical. However you start, as long as it's a zigzag indicating the geometry, it doesn't matter.
Okay.
Yeah, good question. Good question.
I have a question.
Go ahead.
When we're drawing the picture that we just drew with the CL and the OH, do we have to label it or we just draw it?
What do you mean by label?
Like how you're labeling, like you're putting like CL and OH. Do we label or do we just start drawing? Okay.
No, you have to, if I look, so are you saying, do you have to show this?
Because like when we did part A,
we
were labeling everything like CH3 and CH and all that.
Oh, so you want to, but we didn't really label the CHs, did we?
No.
All right, I show, so the termini, the CH3s, you can draw them out or not. It doesn't matter. I like to draw them out myself personally, but you don't have to. The same way down here with the end, the termini, the CH3s, you don't have to really show them, right? But you got to put these in, because if you don't, right, if I don't put a chlorine here, what is that understood to be?
CH.
A CH3. Is that right?
Okay, yeah.
Because the end of every line is a CH3. Is that right?
I have a question.
Go ahead.
So how come we didn't label, I'm really lost with this CH thing. How come we didn't like label our CH? Is it because the pencil markings already count for the CH?
Why didn't I put the CH in?
Right, yeah.
I don't have to. It's a skeletal form. That's the whole purpose of doing the skeletal form. Is look at the Lewis form over here. Right? See how you got all the hydrogen shown, all the carbon shown, all the other atoms shown. You following? The skeletal form is a way to take that Lewis form and reduce it down to something that's cleaner. Okay. So I don't have to show the H's. They're understood. When I put this chlorine here, this carbon right here is understood to be a CH because it's got 3 other things already bonded to it. Here, here, and here. Is that right?
Right.
And the 4th group is understood to be hydrogen if it's not another atom.
Okay.
Does that answer your question?
Yeah, it answers it.
Okay. And it's the same thing down here with the OH group, right? It's this carbon right here has 3 groups already attached. One here, and then one there. So the other group by default has to be hydrogen to fill that octet.
Okay. Okay, I get it.
Go ahead.
Dr.
Go ahead.
Okay, so say we wanted to put determinants in. So since it's only 2 CH3s at the end, at the end, will we just do one line out, and that will be CH3? No.
It's
So
already,
what would that look like?
So I would just write in right here CH3. It's already terminated. If you drew another,
Okay.
You added another line, what you would do is lengthen the chain by 1 carbon.
Oh.
So now it would be 5 carbons instead of 4. So then that would be wrong, right? Because the condensed form had 4 carbons in it. So we gotta have we gotta show some fidelity to that. It's got to be exact.
So the only reason that made the last one because it had 2 CH3, so that would make 4 total. So you had to do the okay. I'm with you now.
So both of these would be wrong button. Both of these would be CH3s, right? For a total of 4 carbons.
Okay, thank you.
I'm glad y'all are asking questions because this is important. If you can understand skeletal forms and how to draw them and how to interpret them, when we do other problems, then it'll make it a lot easier. What about D? What would you do for D? D is in what depiction is D? It's not condensed, is it?
No, it's Lewis.
Yeah, it's in Lewis form. So what would you do to take that from Lewis form to skeletal form?
So you start with your carbon chain.
So take all the carbons out, right? Is that right? So we're going to draw a hexagon just like it is. Yes or no? Remember, every carbon.
Whoever's on the iPhone is giving like an echo.
Right? Every vertex is a carbon, yes? Well, almost every vertex, because one of these atoms is not carbon, is that right?
Right.
So that nitrogen, we're going to put in exactly where it belongs. We're going to put the nitrogen in right here. And the lone pair. Is that okay?
Yeah.
Okay, so that would be that's the skeletal form right there?
No, it's not done yet. What's missing?
Okay.
See all these double bonds over here?
Mm-hmm.
Got to account for that. So we're going to put the double bonds inside the ring for continuity. So we're going to put one here, we're going to put one here, and one here.
I always wondered what that was.
Did you? Now you see you learned something new today. All right? And on this skeletal form, you don't have to put the hydrogens in. Right? But the shape has to match. If this is a hexagon, the skeletal form also has to be a hexagon. And this is this compound right here is what we call pyridine. That's a common name for it. But it's really a analog of benzene, which is a 6-membered ring with 3 double bonds, or aromatic compound. We'll learn that later.
So can you do this like every time you're given like a Lewis structure?
Oh yeah, it doesn't matter what it is. You can do it. Let's go up top. We gotta, well, we don't have time left, but let's do this one. What would you do to that? The limonene, lemon oil. I actually bought some lemon oil to make some fly repellent. It works too. What would you do if you just kind of a shortcut way of doing it would be to erase all the carbons and leave the lines. Though. You understand what I'm saying? Because if you're trying to go from that to the skeletal form, what you want to do is draw that ring out first.
Right.
That's a 6-member ring, right? You see how it's got 6 carbons in it? You got to keep that. You can't divert from that. So you draw a 6-member ring. Let me fix that up. It looks kind of sloppy. Now it looks worse. Sorry. All right. Do we have, so what's attached to that ring besides hydrogens?
We have a CH3.
CH3.
You got a substituent back here, don't you?
Yeah.
And then on this side, you also have a substituent, boom, right there, which is a C that has a CH3 attached to it. Is that right?
CH2.
And it has a double bond, right, to a CH2. Why is that a CH2? Why is this a CH2? Help me out.
Because it's double bonded.
The double bond takes up 2 spaces. So the other 2 spaces are taken up by hydrogen by default, unless there's another atom there, right? So the way you can draw that out, let me fix that because that's sloppy. Come on, eraser. The way you draw that out is you can draw it like this with just 2 lines, or you can actually write the CH2 in. Either way, it's fine. Doesn't matter. So whatever your preference is there. Are we missing a double bond somewhere?
Yeah, in your
on this side over here.
Yeah.
Right.
Right there. So we're gonna put that inside the ring like that. Do you see that? You got 6 carbons, 2, 3, 4, 5, 6. You got a substituent outside the ring. You got another group over here.
I have a question.
Go ahead.
So the carbon that's connected to another carbon that's connected with the CH3 and the double bond to the CH2, are all 3 of those substituents?
No, just this one. Just what's outside of the ring. Just this part right here. Right? This carbon right here is a part of the ring.
Yeah, so are those last 3 or just those 2? Like basically is the CH3 and the CH2 substituents, or is that C a substituent?
This one. Is that the one you're talking about? Right here?
Yeah.
Yeah, that's the substituent. And
okay.
Just so happens what's attached to it is that double bond and then the methyl group that's coming up top. But the carbon itself that's directly bonded to the ring, that's what we would call the substituent. Yes.
Okay, okay.
Yeah, good question.
Okay, Dr. Russell. When you look at D, what form is that in?
D?
Look at D, yeah.
D is in Lewis form.
Is in Lewis form? Okay, so that's Lewis form. And then for skeletal form, because we did the that picture right there. So that's another version of skeletal form?
The Lewis form?
No, the one that we drew.
So the skeletal is another way to depict that molecule.
So we don't always have to do the, how that one had 5 carbons. We don't have to do like, how you the line.
The pencil strokes.
Yeah, the pencil stroke. That's what I'm trying to
So here's the thing about it. That's a good question. So with the rings are true, right? The chains are different because when you first start to write your first stroke, there's actually 2 carbons. You following that?
Okay.
So if I write a pencil stroke here, right, there's a carbon on that side and on that side. That's not the same.
Okay.
A ring is just true to a shape.
So each point would be a carbon.
Yeah.
Okay.
Yeah. Good. That's a good question, though. I'm glad that's a good question.
Okay, I have a quick question. So back to the one that we were just looking at, the one you showed, the one with the hexagon and the nitrogen in there with the pairing. So anytime, let's say, no, the other one.
This one.
Yes, this one.
Okay.
Okay, so I see the 5 carbons, and So since nitrogen is a part of the bond, you just kind of write it in there just to show that it's not a carbon, it's a nitrogen.
Yes.
So that's just with anything, like you just add it in there, and that's it.
But the ring itself has six members, right? It just so happens that one of them is a nitrogen.
Okay.
Right? I'll give you another example. Let's say we had a ring like this. I know we got to go. We're like 8 minutes over, but that's fine. If y'all are still talking and asking questions, then I'm going to answer. So let's say we have a ring like this, right? Where this is carbon, 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 and then this is oxygen. You following?
Yes.
It's the same thing, right? I just write a 6-member ring out, and then I replace one of those carbons with oxygen. It's the same thing.
So it's just rather than labeling everything, you're just labeling the one that's not carbon because it's already insinuated that the bond is going to be carbon anyway.
Yeah, if this wasn't oxygen, it would be understood that there was carbon, right?
Right.
So that's why you have to put the other atoms in if they are present. So in order for me to know that that's oxygen, I got to put it in. I can't just leave it.
Okay.
Then I can't assume that it's oxygen, but I can assume that it's carbon if nothing else is there.
Okay. And also, like, I know right now we're just learning how to put stuff in like skeletal form, but after we basically master that, do we need to like on our own time teach ourselves how to like turn something that's in skeletal form into like, Lewis structure?
I would practice as much as possible. Because you see these other questions down here, 166, 160. You don't see any Lewis forms down there, do you?
No.
Yeah. So everything when you take an exam, you're gonna see the stuff is gonna be written out in skeletal form. So you need to master how to interpret what a skeletal form actually means, right? Like look at 166A. How many carbons are there?
168. There are.
Every vertex is a carbon.
I want to see. Right.
So it's 6 carbons in that ring, right?
Right.
What about B? Where are your carbons in B? If it's not written out, it's understood that at the end of every line, right, is a carbon.
Right.
And then that's also a carbon. Is that right?
Yeah. And then there's a oxygen somewhere at the top.
Yeah, sure.
Yeah.
Are you following? So look at this molecule. What about that? Where are your carbons in C?
There's 4 carbons. And then
here.
Well, I guess there's only carbons. There's no other label.
Right. Yeah. Exactly. Right. No other atoms are listed. So everything is carbon or hydrogen.
Right.
So
what's this plus sign at the end?
We're gonna talk about that. It's actually a carbocation. It's a carbon with a positive charge. We're gonna talk about that when we start talking about formal charge and stuff like that, which would be Wednesday.
Okay.
Yeah. But yeah, so do you see the importance of the skill?
Yes.
Yeah. If you got it, that's why I'm spending time on it, trying to learn how to interpret these different structures. So when you get to something like this, right, you ain't panicking. Right? You know that that's a carbon. You know that that's a carbon. You following?
Right.
Yeah. So we're gonna put as many reps as you can get them. That's why I put practice problems in the syllabus. Did you ever play sports?
For me?
Yeah. Did you play sports as a kid or as in high school?
Yeah.
What did you play?
I played basketball.
Basketball. How'd you get better at free throws?
Practice.
You can't get around it. Free throw, how'd you get better at your drop step or your jump shot? Right?
Practice.
Everything is reps. Organic is not it's an easy class, but it becomes easier the more reps you do. Because if you're not spending time trying to figure out if the carbon has a hydrogen on it, then you can go into something more complicated. Right?
Gotcha.
Yeah, always get the reps in. All right, I think we got to stop because we about like 13 minutes over.
I have a quick question.
Go ahead.
So B would be a SP2 hybridized.
You
Like
let
if
me
we
take my
could
screen down and everything.
Oh my God.
You
If
see me
we
take the screen down.
don't know the
Hold up.
Okay.
B, that's good because I'm definitely gonna incorporate that in. Come on. You said B on which question?
166. Cause I was
Oh
trying
yeah.
to see
You
how
talking
you would
about the
have
little
different
carbon?
test questions. Yeah, like
This carbon right
you
here?
ask something like that. Yes.
Yeah, it is SP2.
Okay.
How can you tell?
Because of the geometry.
It's
and
trigonal.
scale.
Do you
Yeah.
see now why that's important to know that that's trigonal and why they didn't just draw it like this?
Yes.
You following?
Mm-hmm.
All of that stuff matters, but it's stuff that normally gets glossed over.
Right. Right.
I mean, once you understand that, then you understand why it looks like that.
Mm-hmm.
What else can you tell about it that is SP2?
Um.
Look at the carbon and look what's bonded to it. How many groups are bonded to it? You got an
That's
oxygen up
30.
here, a carbon over here, and a carbon over here, don't you?
Oh yeah.
That's
Yep.
three
Three.
groups.
Oh yeah. Yep.
What
Yep.
else? It has a pi bond to it too, doesn't it?
Yes.
Yeah. You see how all that stuff converges
Mm-hmm.
in an
Mm-hmm.
example that's not even asking you about hybridization.
Right.
Yeah.
Right.
So my biggest piece of advice, if you want to master the course, is to
Mm-hmm.
practice.
Okay.
Practice, and answer those questions that's not being asked. Oh,
Right.
this is SP2. So every time you do an example like that, you might want to have a checklist. Oh, what's the hybridization
Right.
of that? Oh, how did I get this charge over here? Oh,
Mm-hmm.
why is it shaped like this? You understand what I'm saying? How many
Mm-hmm.
carbons did you change?
Right. Right.
If you do that with all your examples, I promise you,
Mm-hmm.
will ace this class.
This
Okay.
is crazy
Thank
because
you.
this should be a prerequisite to the other classes.
Say that again.
I was saying, I feel like we're being taught backwards. This should be a prerequisite.
Not really, because you did learn geometry in Chem, part 2.
Well, yeah, true.
Yeah, you learned geometry. You learned vector theory, right?
Yeah.
ESPER, valence, shell, electron pair repulsion, EPR, something like that, right? So you learned about tetrahedrals, and you learned about octahedrals, and you learned about linear and square planar. It's just now applying it to a different concept, a different range of atoms. That's all you're doing.
Oh, so can we go ahead and upload these?
No, because we're not done yet.
Okay.
We got a lot of questions left. I just zoomed in and so you won't panic. But we got a lot of questions left to answer.
So on Wednesday we're focusing on resonance.
No, we're not doing resonance until the next module.
Okay.
Yeah, it's listed in the first module, but it's actually, we're going to cover it. The videos, I think, are in the next module. I think.
Okay.
I'm gonna double check now, so I won't make myself out of a liar.
Okay.
But I don't think resonance is in this module. I know it's not on this handout,
Mm-hmm.
but that's another thing that we're going to spend a lot of time on because it's very important. If you master resonance now, when you get to part 2, you're not backtracking. You're not thinking about it. You're just doing it.
Right.
You want all these skills that we're doing, that I'm spending all this time on, doing it so it becomes second nature to you.
Right.
So you look at this molecule and you're not saying, oh, I wonder how many carbons are in that ring. You already know, because every vertex is a carbon, right?
Right.
Oh,
Right.
is the OH a substituent? No, it's a substituent that's attached.
Right.
But this carbon right here is the one that's attached. You following?
Yeah.
All those skills I'm trying to help you to build up now, so that we don't waste time when we get to the heavy stuff. We'll figure out the basic stuff.
Right.
So lay the basics down now, and then when we get to heavy stuff, it's not as hard. Because this is not something you having to think about.
Right. Right.
So we're gonna rock and roll. We're gonna get some things accomplished. And yes.
I have a question. So you keep saying like this is the basic stuff. I'm gonna be 100% real with you. I've been lost all class. It's just I feel like maybe like with the chemistry classes I've taken, I really didn't understand the basics of drawing these diagrams. So like it's all new to me. Do you have any suggestions as to like to be able to catch up Like, do I watch YouTube videos? Should I go back to my general chemistry book and just rewrite all my notes, or
I wouldn't go that far as to go back and rewrite all of your notes. But if do you have a book for this class?
I ordered it through the bookstore. Like, the lady had to request that, but it's not here yet.
Okay, so if you don't have a book, my suggestion would be to, like, the topic, whatever topic you're having confusion about, or whatever topic you're lost on, I would Google that topic, right? Or go to this website right here. Let me show you. Because I think did I pull this up for y'all the last time? Master Organic Chemistry. You can go to this website right here. And then don't be afraid to ask questions, because there's no such thing as a dumb question, ever. Wait a minute. Yeah, it's not .org, my bad. This website right here is awesome. If you do a search and you say, let's see what he has for skeletal forms, right? So all this stuff down here, resonance structures, breaking down carbon, you can look through IUPAC nomenclature. This would be a great resource right here, because nomenclature is just naming. But in order to name, you got to know how to interpret the structures. So there's a lot of different things that you can do to catch up, besides going back and rewriting your notes. But
Okay.
don't ever be afraid to ask questions. Anything, if you were going, yeah, that's fine, no problem. For now, Brittany, yes, but we're not done yet. Yeah, but if you ever have questions, just ask. And if you need some help, additional help, just email me. Hey, I need to have a Zoom session. We need to do X, Y, Z, because I don't understand this. And then we can go from there.